The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Thank you very much, Mel. Well, as you can read here, the topic of this presentation is whether we can use acoustic emission to detect alkali silica reaction as a test method. Now, as Anol mentioned, this is a work that I did at Purdue University during my PhD studies. I would like to acknowledge my co-authors, Robert Strag, who is a graduate student at Purdue University, Javier Castro, he's at Catholic University, Chile. Currently, he's an assistant professor, and, of course, Professor Jason Weiss. Now, this is the outline of this presentation. I will go through 3 parts here. First, I will introduce the concept of model system, just to take a look at the acoustic emission and whether we can detect cracking due to aggregate expansion. The purpose of that, of course, is to show that we can use acoustic emission to detect cracking due to expansion and address a couple of the issues that we might have by using acoustic emission. For example, having coupling between sensors and sample. After that, I will go into a mortar sample and show some of the preliminary results we have on use of acoustic emission to detect cracking due to ASR in mortar samples, and then briefly talk about the effect of geometry and temperature as it relates to the mortar sample test that we had. Now, the concept of model system is pretty straightforward. Here, what we are trying to do in composite material, we are making a composite material. We are replacing the aggregate that we have inside the mortar with spherical inclusions that are made of plastic called acetal. Acetal has a pretty high coefficient of thermal expansion compared to cement paste, and then we can use thermal loading to basically cause cracking. Now, the entire idea is we are having a controlled experiment and control rate of cracking, and we want to address 2 issues. We want to address, 2 issues, and one of them is whether we have a good coupling, and the other one, basically, we want to detect cracking. Now, the idea is shown here schematically. We have a spherical inclusion. Again, we are using a spherical inclusion. I will address this when we move to mortar sample. In mortar, we almost never have spherical inclusions. Then we increase the temperature from 23 C to 30, and we cause cracking inside the sample. The acetal aggregate shown in that image on the right-hand corner of the slide. This is the experimental setup. Now, in this experimental setup, we have a composite material. Basically, these are the composite samples made of cement paste and acetal aggregate, schematically shown over here. We have a coupling agent, and this is an acoustic emission sensor. You can think of it as acoustic emission sensor as a very sensitive microphone. There's a little more than microphone into it, but you can think about that we are really listening to the sound of cracking. And then based on the, for example, characteristics of that, based on duration, amplitude, and so on, we can have a pretty good idea what is happening inside the system. As a control, we have a piece of, this has to be aluminum, piece of aluminum with coupling agent with a sensor on top of that, and a very complex fixture made of pieces of steel and basically rubber mat and foam just to damp the vibration, and it is encapsulated inside a temperature control and relative humidity control chamber. And we have a thermocouple inside another piece of sample just to measure the temperature inside the specimen. Now on this slide that shows the result of this model system, or basically a physical modeling of the system, the solid red line is the temperature. We have two types of composite, results from two types of composites shown here. One of them inclusion or acetal aggregates that have 3 millimeter diameter, and the other one is 5 millimeter diameter, and a piece of aluminum that we are using as a reference. The first thing that I want to take away from this is that we can see some acoustic activity regardless of the aggregate size after some increase in temperature. For example, if I go back here, approximately after 4 degrees of temperature change, 4 degrees C temperature change, we can see that we can listen to the sound of cracking. The other thing that I want to take away from this is that I do not hear anything on the aluminum. It's because it's basically what we are trying to show here is that there is no cracking, of course, inside that, but the objective is here to show that there is no change in the properties of coupling agent. We used quite a number of this coupling agent until we came up with this one. And you might see here that the larger aggregate has less acoustic activity. This is because we are looking at the same volume of the material, and more number of aggregates are in the when we are using a smaller aggregate, we are having more number of aggregates inside the material, so we have potentially more cracking. But it should be the proper way would be to normalize this. And of course, during the unloading the sample, we don't hear anything from the material because we are not introducing any cracking. Now, these are basic observations that we could detect the cracking caused by aggregate inclusion expansion inside this composite material, and we saw that we found a good coupling agent that we don't have any issues with sensor sliding on the sample and decoupling and so forth. Now the next part is the actual the experimental setup. We are testing mortar samples. Again, here the aggregates are not spherical, and the other difference between the model system and the system that we are looking at, the mechanics are similar, but the mechanism of expansion is very different. So we are looking at mortars directly here, and cracking in model system that we have, the cracking can happen at the interface and the cement paste. Well, here we really can have cracking inside the aggregate also. The mortar sample we are using is a water cement ratio of 0.47, aggregate volume content is 55%, and the aggregate is a Job aggregate that Noel talked about this aggregate. This aggregate is highly reactive, tested by multiple laboratories across the country. After only 3 days, it passes 0.1% expansion. This is a test setup that we have for acoustic using acoustic emission. We have a cylindrical sample here that has a 4-inch diameter. I will discuss the implication of the dimensions of the sample later. It is 14-inch tall, and we have 2 acoustic emission sensors that are installed on top of 2 pieces of steel that we call the waveguide. Now, the entire idea is acoustic emission sensor is made of aluminum, and if we put them inside one normal NaOH, probably they will disappear within a couple of hours. And we have another piece of steel on top of that LVDT sits on this, and that is for having a simultaneous measurements on acoustic emission and expansion of the material. It's installed on a steel fixture. The entire thing is placed inside the chamber. Basically, we have sealed this. We have made this fixture at the bottom to just have a more accurate type of length change measurement on the sample. This is the actual sample. You can see these 2 waveguides, which are nothing but high corrosion-resistant stainless steel, and another piece here. During the experimental preparation, we just try to keep the sample sealed to avoid any evaporation. And the top surface of these are epoxy coated, of course, and the main reason for this was later on, if we want to do modeling on this, and for example, moisture transfer, we really want to look at the one-dimensional systems. Now, experiment is done in a solution that's similar to 1260, but the actual experiment, the temperature is 38 degrees. When we enter into the temperature part, I will discuss this. And then before start of the test, the solution and experimental fixture was set in the chamber for a long time to make sure that it is very close to the environment. And after we mounted the sample into the fixture, we let it sit for 6 hours. The threshold for acoustic emission was set at 42 decibel. This is mainly because we really don't want to hear anything from the chamber or from someone playing around in the lab. And we are measuring passive acoustic emission that we are really listening to the cracking and wave propagation that's resulting from that for up to 24 days. Here are the results from acoustic emission testing on mortar. The hollow circles here is a length change expansion, and the result of that is shown on the y-axis. On the right, on the x-axis, you have time in days, and on the y-axis on the left, you have acoustic emission energy, which you can interpret this as an energy that's absorbed by the sensors. Now, there are a few features that we see over here. We have a period that's very little acoustic activity, then we have an increase in acoustic activity, then there's a dormant period, for lack of a better term, for acoustic activity, and then sudden rise in the acoustic activity, and then it plateaus off at the end, approximately after 18 days. Now, we are really looking at this more closely, but at this time there are possible explanations for this. The first feature that we saw this in quite a bit of sample when we repeated this, and this happens around somewhere around 6 to 8 days, and we think this is due to aggregate cracking that's happening inside the material. This is the possible explanation that we have due to aggregate cracking is basically based on the literature survey that we have done and based on the difference in the characteristics of the wave that we absorb, that we capture during this period versus this period. After this, we have a dormant period that we think this is because we have now cracking happening inside the sample. The gels have more space to deposit, and basically we have more space inside the system, and the gels are being developed and deposited in those and are not causing any more cracking. After this, the gels are absorbing water and they're causing more cracking inside the system. That is basically the cracking not only due to cement paste cracking, but there's interface cracking type of behavior. Now, these are based on the differentiation between the type of cracking that we see here and here is the first one, the magnitude of this cracking, and the second one is a characteristic waveform of these. After that, we enter to the region that's really, we don't see much of acoustic activity. Again, this might be because we have a lot of cracks that are opened inside the system, and then the gels are being deposited into this newly formed cracks. And also, there are more cracks inside the system, so when the new crack happens, it has harder time passing through all these new interfaces. So there is more elastic wave attenuation inside the system. And there might be some gel formation at the interface of the waveguide and the sample that's sitting there and basically causing a lot of attenuation and reflection of the waves. I just warn you over here that this experiment has been done at 38 degrees, not at 80 degrees, at 1260. But if you look at the 1% expansion criteria for this material at 38 degrees, we are looking at something around 28 days. If you look at the severe cracking of the sample, or energy that we captured, acoustic energy captured inside the sample, we are looking at somewhere around 14 days. And if you look at the first rise, we are looking at something around 6 to 8 days. So this test basically is potential for rapid detection of ASR in mortar sample. Now, we use a larger type of sample and we use a different temperature. I just wanted to briefly discuss these effects. One of the studies that we did to look at this a little closely is looking at different size of sample and different geometry of sample, and to see what implication that has on our test. That you can see we have a full range of cylindrical sample and prism samples. Now here are the expansion results. Again, this is at 38 degree. And you can see that the shape and size of the sample really affects the rate of the expansion. Now we have, for example, 1-inch diameter cylindrical sample, which is over here, and 1-inch prism, which is down over here. The difference between prism sample and cylindrical sample is, of course, the fact that in cylindrical sample, the flow of ions or diffusion of ions is more of one-dimensional flow. Of course, when we change the geometry of the sample, we change the volume to surface ratio of the sample. This is the same result. On the x-axis, you see inverse square root of diameter, which means over here are the larger sample, and over here are the smaller samples. Here, this is on y-axis, you have expansion. You can see that at any given age, for example, let's look at it 29 days, the sample that has a smaller diameter has a larger expansion compared to the sample that has a larger diameter. And this inverse square root of diameter really comes from a composite model and taking into account the transport inside the composite, inside the geometry, cylindrical geometry. To look at the effect of temperature here, we performed the experiment at 38 degrees, but when we have the same aggregate in a mortar according to 1260, you can see that the expansion is really severe. The aggregate is expanding very fast at 23 degrees and 38 degrees. The results are not shown here, but you can actually use an activation energy approach, and they really follow the activation energy approach. Now here are again, based on this, we performed the experiment at 38 degrees, and we used this on a larger sample. Based on the aggregate that we have, we really slowed down the system, and this was to have a much controlled system. We need to do more basically investigation and research on the effect of temperature and geometry of the sample. Now we saw that the acoustic emission can capture cracking due to aggregate expansion and ASR. We saw different stages, or for lack of a better term, dormant period were observed, and more research is needed to really better understand what is happening inside the system. We saw that the cracking could be captured earlier than expansion, and this physically makes sense because for expansion we didn't need cracking. Waveform analysis can be used in this to really differentiate between aggregate cracking and cement-based cracking. We looked at the effect of geometry and temperature, and we saw that they have a significant effect on the rate of expansion, and of course more experiment and research needed to really understand the effect of this on acoustic emission testing. But what we really want to get across here that this acoustic emission is really potential as a test method for ASR testing. Thank you.